Hi, in this video I will explain how to use the Simulink model that you can download with our new paper. This is the page in ResearchGate where you can see our new paper that we have published in Transactions on Industrial Electronics. And here you can download a PDF file of the paper. So in this paper, we proposed a novel method for estimating the stator resistance in each of the phases of a six-phase induction machine, either in healthy operation or under an open phase fault that is being tolerated. Here you can also download a Simulink file that is the one that I'm going to explain now. So if you click in linked data and then in this link, you can download here the file. So let's do that. And now let's run the model. So this is the Simulink model. You have several parts. In this part, you have the model of the control and the algorithm for resistance estimation, which is included in this blue block. You can see that it is triggered by a signal that is executed at a certain sample time of 10 kilohertz, because this variable is defined here in the model settings, model properties, callbacks, init function, and you can see here that there are several variables that are defined. This is executed at the very beginning of the simulation when you run it. So here you can see that the period of the controller and of the estimation algorithm is 100 microseconds. So this means that the sampling frequency is 10 kilohertz. So here you have also some parameters of the machine, and also the vector space decomposition transform, which is defined for a six-phase symmetrical machine. So that's regarding the blue block. And here we have the model of the six-phase machine. So if you do double click on it, you will see that here you can define what's the nominal stator resistance, and also you can define some additional resistances for each of these phases, because we want to test a case in which the stator resistance is imbalanced because of, for example, some high resistance connection fault or of different temperatures between phases, although in that case the difference would be much lower than this, of course. We want to test that the proposed method is able to estimate the resistance of each of the phases effectively. Here, what we do in these blocks is that we compare what are the resistance estimates and the actual resistances. Okay, so the input of these simulations, this is a signal that we set to 1 when we want to start the estimation process. So we don't have to estimate the resistances continuously because they usually in practice change very slowly. So we only inject the signals for the estimation from time to time. For example, every 360 seconds, which means every 6 minutes. So you could change that this if you want, but in any case, just keep in mind that usually you don't need to do it very frequently. In this block, we set if the machine is considered to be in healthy conditions, or if we consider that there is an open circuit in one of the phases because of a fault. In that case, we would set it to 0. So right now it's set to 0, so we have an open phase fault. Uh, in the open phase fault is applied to the first phase, to phase A. Here we also have the reference for the speed, so we are considering the same value as in most of the results in the paper. And actually, all the values in this model are the same as those used in the experimental setup of the results of this paper, so that we can compare them more easily. Of course, you could feel free to change any of these parameters, and also those of the machine and the control. And here we are also inputting the stator current and the speed to the controller, because we have also a closed loop speed control that is in charge of keeping the speed constant. Okay, so here inside the blue block of the control and can see that indeed we have this speed controller, which is a PI speed controller. We are not going much into detail and those for those things because that's not the focus of this paper. Here we have also the generation of the current references depending on whether we are in healthy condition or in open phase condition. But that's also not the focus of this paper. Those references are for the AC components of the currents. Feel free to check our previous papers about that if you want. And here we have, of course, the vector space decomposition, changing the coordinates of the signals, and the components in each of the VSD subspaces, of course. And this block is where actually we can find the proposed method. On the one hand, we generate the DC components of the current references in the XY plane and in the zero sequence axis. And we also estimate, on the other hand, the resistances. So all of that is done by this proposed method, which is contained within this block. And you may also note that we don't change the references in the alpha beta plane, the main plane of the machine, which is responsible for the flux and the torque. We are not injecting any DC signals there because we don't want to cause any torque ripple of method. Okay, here we also have some inputs that are explained in the paper, the magnitude of the DC current that we want to inject, the time that each of the three injection intervals lasts, because as explained in the paper, there are three injections intervals. Each time we are going to estimate the professed resistances. Here again is the sampling period. This defines the quality factor of the notch filter that we have in the method. And here we have the bandwidth of the low pass filter. All those things, you can see them here, okay? So each time there is a rising edge in the trigger signal that we uh, saw before, then it starts all this process generating the time sequence for the injection. Here it estimates the DC current references, and then here it estimates the resistances based on the pole voltages, and it takes into account the fundamental frequency and the parameters of the filters that these two blocks are the filters. Here we have the filtered voltages, so these voltages are input to this part of the method where where we sample and hold each of the voltages at the right moments for the method to work. Then we combine all of them by using the equations 10 and 11 of the paper, depending on whether we are in healthy condition or in faulty condition. So we generate resistance estimates. Okay, so that's the main purpose of this block of this paper actually. Now here you also have some other things. For example, in case you were going to take into account the convergent nonlinearities because of the dead time and other effects, you could compensate them by using this block, which is taken again from the reference 15 of the paper. Okay, that's not part of our proposal. And here you can see the current control. So we have in each of the subspaces, we have resonant controller for the fundamental component because it may be imbalanced during the case of resistance imbalance. So we need to compensate that, impose the actual current references for the fundamental component, which may be actually also imbalanced in the case of an open phase fault, of course. And also here we have the PI controllers that are responsible for tracking the DC components or for rejecting the DC disturbances in the planes where there are no DC current references like in the alpha beta plane. Okay. Finally, we transform again the VSD components of the voltage references to the per phase signals in order to send them to the PWM model, which for simplicity is not implemented. The PWM is not implemented here in this simulation for simplicity. You could add it if you want, but um, is not actually necessary to see the main theory of this method. Okay, so let's run it. So here, if we go to run, And also see that here we have also defined the initial speed of the machine and load torque. So that for the open phase fault, we the rate that load torque so that there is no overheating because of the AC current in the phases. And also here we have the machine. If we look under the mask with Control U, we can see what's inside this machine model. We can see that we have the this block contains the model of the machine, any resistance imbalance. So what we do is that we add here these resistors, and in which we can add the specific resistance that we want to add for each of the phases. So here, for example, here this is very large because this is used to emulate the open phase fault when this variable is zero. Okay, so in case it's zero, we are using this resistance for the phase A, and otherwise we use this other one, which is the one that we are setting in the dialog of the mask as we have seen. So, okay, so here we use a minimum and maximum functions because we want to make sure that this additional resistance is between vertically 0 and 100. And here we see the additional resistances for the other phases. No, okay, let's see. Okay, so the simulation has finished running, and we can see that actually the estimated and the actual resistances they are very close to each other, so we can see that the method actually works. This is under an open phase fault. Okay, we may see here some other variables. The current, we can see here that the current. Okay, so at the beginning we have the imbalanced currents because these are the optimum current references for minimal losses under an open phase fault in phase A. So phase A, the yellow one has zero current, and we can see that the instant of 2 seconds, it starts to inject some DC signals. So peak values increase, but not too much. And then the DC references are changed here at the time equal to 4 seconds for another 2 seconds, and then it is done again. So we have these three intervals with different DC and different kinds of this injection, and finally we remove the disinjection. So we have again same currents as at the beginning for fault tolerance with minimum losses. We may also see here the DC components of the current. The signals that change very abruptly are the DC components of the references that we generate with the proposal. The ones that are smoother are the filtered measured currents, which tend to match the references, as you may see. So here you can see how the DC components are different in each of the three intervals in order for the method to work, okay? And we can also see the DC components of the voltage references, which are very different from each other because of the fact that we have a significant resistance imbalance in the speed. And we can see that the speed doesn't change in spite of the fact that we inject DC signals here. Here there is a transient at the beginning because at the beginning the speed control has to work in order to reject the load torque. Okay, so that's normal. But mainly we can see that here when we inject these signals, there is no change. Or the change in speed is negligible. I mean, it's almost nothing because that's taken into account in the design because we avoid the injection of this signal in the alpha beta plane. Okay, we can also see the torque. So yeah, at the beginning there is this transient, of course, because the control has to make the torque of the machine match the load torque. But most importantly, then when we inject these signals, there's practically no change in the torque. Okay, there's some small and short disturbance, but that's because during a certain time the current control needs to reject the DC part of the current that is here in the alpha beta plane, and of course it cannot reject it immediately. It takes some brief time, so that's the reason for that small torque disturbance that we saw. But anyways, the method actually provides very small and brief torque oscillations, and we can neglect it. And also, it's not the focus of this paper to design a very high performance current control. So you may further improve the current control, or you may use a different controllers like model-predictive controller, which are not the focus of this paper if you are worried about that. Okay, so here you may also note that we include two different alternatives for the tuning of the gains of this PI controller that is responsible for rejecting the DC component in the alpha beta plane. So if you set it to 1, you have a faster DC rejection because the gains are higher. Okay, you can see here that the gains are lower down in here. And also in addition, this when you set it to 1, you are including an active resistance, which helps to improve the rejection of disturbances. So this also helps to reduce the effect of the DC components on the alpha beta plane. Okay. But in the experimental results of the paper, actually we used 0 here, a worst case scenario. And as we saw in the paper, it also works very well with torque in that case. Okay. So now we can try to set this variable to 1 so that we test the healthy case. Let's run it now, and we will see that it is also able to estimate the resistances in that case satisfactorily. So we can see here that indeed the resistance estimates also match the actual resistances in case of healthy conditions. The only difference is that here now the first phase A, is not infinite anymore, so it matches between the estimates and the actual resistances. Okay, so now we can see here again the DC components of the currents, which also match the actual currents with the reference DC currents. And here we can see also the DC voltages, which are imbalanced because of the resistance imbalance. And here we can see again that the speed practically does not change during the disinjection, and the torque, other than the initial transient that is normal, we barely have any disturbances in the torque when we inject the DC signal. So this it's properly designed so that there is no DC components in the current references in the alpha plane. So now let's try something else. Okay, we can set it again to faulty conditions with an open phase fault, and then we may change these variables so that you can see that it's actually adaptive. So let's um, put here, for example, 0, 0, and here 9, and here 1.2, and here, for example, if you want to test something very exaggerated, was for example, by 28, which is too much, but in this manner you can see that it's very general, the method, and robust. And here, let's 2, for example. So let's run the model again. So here we may see that the resistance estimates are correctly adapted. So they keep matching the actual resistances. So the method works properly. For further details, of course, please read the paper and see the explanations and the experimental results here. I hope this method is useful for you, and also this video has helped in the understanding of this method.